So PLC it stands for Programmable Logic Controllers. A lot of people call it PLCs. Some people call them programmable controllers, but that's not what PLC stands for, right? Y'all understand? I think one of the topic quizzes asks you what PLC stands for, and one answer is programmable controller, and another answer is programmable logic controller. And if you answer program controller, you get it wrong, right? Even though if you say that. History of program controllers, we're not going to do much about that. Discuss the benefits of PLCs over electromechanical relay systems. Distinguish between fixed and modular PLC devices. And we have both of them in here. Discuss the different types of Motorola microprocessors. Probably not. We'll talk about general microprocessors, but I think this is actually from McGraw-Hill. Goodhart Wilson, I'm sorry. Explain the difference between types of memory inside the PLC. So we'll learn about the random access memory and also the different types of ROM memories that we can run into. We'll talk a little bit about the address encoder. List of major components of the PLC power supply. We probably already know that, but we'll get a little more and describe Allen Bradley program controller devices. I don't know exactly what they mean there. So, first of all, a programmable logic controller. First of all, we'll look at different types of portals we can have. So basically, we'll look at this later on, but the parts of a computer. But we always have to get information. A computer would be no good if I couldn't get stuff into it and get stuff out of it, right? Does that make sense? So we communicate with the computer through devices, what we call portals, or most people just call ports. And of course, the two primary ports would be, we actually have three primary ports. We have input ports. So what's the input port on your cell phone? This is a computer. So what's your input port on your cell phone? Huh? No, that's power supply. It's what? It's a screen, right? That's a touch screen. That's your input on yours, right? What's your output? Speaker would be an output, and also your screen output, because this is a screen. So this has actually got a layer on it that's touch sensitive, right? And then of course it displays. So, but these guys don't connect directly to the process, the actual things of the machine. It goes to a portal that we call input ports and output ports. So the portals can either be digital. So these are all digital, right? You understand that? So because you touch, what happens when you touch it? It's got what we call metrics there of thousands of sensors. When you touch it, you make a touch between a group of rows and a group of columns. And then the phone is scanning. When it picks you up, it says, okay, you're what? You're right here at this spot. But it's still only ones and zeros. It's just a bunch of ones and zeros. Ones and zeros. That's representing where your finger's at. Does that make sense? So digital means digital. Book calls them discrete, but most people are going to call these digital, or they're going to call them binary ports. Probably digital is most often. These type of input or out, these types of devices are either what? They're either off or on. True or false, 1, 0. Then sometimes we have to deal with, so it's either there or not there, right? True or false. But a lot of times, especially computers or program controllers, have to deal with what we call analog signals. Analog signals are something that varies all over the place between set limits. So analog would be like temperature, a lot of lighting and stuff like that. With speed might be analog, right? You understand that? So some of your PLCs have analog ports on them. Some of them are on there by default. Some of them you have to order them and put them on there yourself, right? Does that make sense? So analog signals and digital signals, y'all understand the difference? So predominantly, the devices we're going to deal with are digital. All the devices that we're going to deal with in this semester are actually digital. So This guy's got 2 analog inputs on him, but the other one that we're going to deal with, or depending on where you get, the 1100 PLC only has digital. So this is basically different with digital. Digital is ones and zeros, trues, falses, all phones, right? You understand that? And then analog has the ability to change over a range. So like the temperature, so the high today was, I don't know what it was, the low would be. And while it changed between that, it changed at an analog rate, right? You understand that? So if I wanted to measure temperature, then odds are I'm going to have to do it through analog, right? If I want to measure digital, then like push buttons and contacts or anything like that that we talked about, those are all digital devices. So predominantly digital, like I said, the only thing that we're going to deal with this semester are the big digital devices. So we're going to turn lights off and on. We're going to simulate relays and stuff like that. So this is the basic makeup of a computer. Usually we have a power supply, but most of the time when we talk about a computer, that's easy to understand. And then we have a processing unit, right? You understand that? And then we have inputs that connect to the system. Now this is, in computers, it's different. In PLCs, they talk about the central processing unit in the computer. And we'll see what makes up a computer here in a minute. So when they say this, if I was talking about my computer at home, and they say, what CPU do you have on that? I would say I have a Xeon, AMD Xeon, quad-core processor. And say, okay, here we have this unit right here. If you can see this is the CPU. If you can see this box is called the CPU. You know, there's a lot to a CPU in a computer. In PLC, the main processing unit's got everything in it that makes up a computer. They call it the CPU. That's just the way things are. So in computers, the CPU is one component of a computer. In PLC, the CPU is the computer, right? You understand that? So we'll look at the difference. What we do here is all the portals and everything are built into it. So, can you see this? I might need to put it on the camera. So, oops. So this is the Allen Bradley this is the 1000 series, and of course this has an internal power supply, so it hooks directly up to AC. So that's L1 and L2 is right there. That would be, so it's got an internal power supply, and then this up here, these terminals right here, these are the inputs, and these are all digital inputs, right, or what the book calls discrete inputs. So this right now has 10 inputs, discrete inputs, and it's got 1, 2, let me just say 1, 2, 3, 4, 5, 6 outputs. That makes sense? And they call this the what? The CPU. Everybody okay? What do you mean? This up here, they got eye. Can you see the eye? It'll focus in. And we'll talk about the commons and everything later on. If I can get it to focus, it'll focus in beautiful while I do it. Because that's what Allen Bradley decided to do on this. I mean, it's a good question, but this is what this is. That's the one of the things. That's the one of the things that you consider when you buy a PLC: is how many inputs and how many outputs you need. And then is it expandable? Is it expandable or is it fixed? So we call this, it's in the slides, we call this a fixed PLC. A fixed PLC, you get what you buy. Everybody understand that? So it's just like now when you go out and you buy a smartphone, you get what you buy. If you wanted something else, you'd have to go out and do what? Buy a new cell phone. So that's the way this is right here. You get what you buy. So this would be specified in the specs that this guy here has 10 inputs and 6 outputs. If that don't do what you need to do, you do what? Buy another one that does what you need to do. And that's one advantage of these guys over here, these modular PLCs. So I still have a desktop computer at home. And I still use a desktop computer. And why? Because I decide what's in the thing, and I know how if it don't have what I got, then I can add it because I know how to do that. We just built our grandson a gaming computer, a desktop computer, and we did what? We put what we wanted in there. We didn't buy one. We put what we wanted in there, and of course, if we need to add stuff to it, we can do what? Yeah, that thing supports 3 video cards. It's a Xeon. Oh no, it's a Radeon graphics in there. So this shows an analog, but it shows it in dashed lines because normally this right here is what this is usually optional. Unless you get a modular, what we call a modular PLC. This makes sense. So we basically have 2 categories of PLCs. We have what we call a fixed PLC, which is what I just showed y'all. Instead of me putting it on the camera, let's pass it around. Here you go, Kevin. This is actually a trainer, so that's why it's got all the push buttons and lights on it. But the little PLC is right in the center. And that's a fixed PLC. So the advantage of a fixed PLC, it's a lot cheaper, but what? You can't add to it. What you buy is what you get, and these are still very popular, doing small applications, right? You understand that? So very, very popular. Number of inputs and outputs ports cannot be expanded. Number of output ports cannot be expanded. The amount of memory in it can't be added to. The way the memory is organized can't be changed. So it's pretty interesting. But these things are still very popular. The 1100, the 1000 is not being made anymore. It's being replaced by the 1100 right here. The 1100 is still out there, and it's very, very popular. So fixed PLCs, y'all understand? What's the advantage of a fixed PLC? Cheap. The biggest disadvantage is you can't upgrade it if you need to add stuff to it, right? So the next type we have is what we call a modular PLC. That's this guy right here. So let's pause it and let y'all come up here and look at it. Slick. And like I said, a lot of your PLCs are just like this. So every PLC that we have and the ones we're getting, we're going to start getting some Complex Logics. They run off a new version of Allen Bradley called RS Logic 5000. These still run off of RS Logic 500, which is the one we'll teach. But it's just like buying a new car. So when you buy a new car, you know they all do exactly the same. It's just got to figure out how this car does it. So once you learn how to program in one ladder language, then you can go between PLCs. And believe me, you can. The first PLC that I programmed was a Square D, and it programmed in ladder language, and those are not even around anymore, the ladder language. But I've adopted every one of them. So this is basically the makeup of a microcomputer, but it's not. This guy didn't quite get it right. So let's go. So this is. Let's see if I got it in here. So this is basically what a computer consists of. It consists of a unit that was referred to as a microprocessor. When I first got into computers, the computer I worked on, put out by Lockheed, by the way, and it took 3 circuit cards that were about this long and about that wide, so there's about what 12 by 5 or 6 inches, and it took 3 circuit cards to make up what we call the central processing unit. But over time, what happened, of course, is, and we still run into these in these supercomputers, because what happens when we start reducing the size down, what has happened is we don't have the ability to run them as fast. What happened is they eventually came up with a method where they could take all these circuit boards and integrate it on a single little chip, and we started calling these microprocessors. Some people still call them CPUs, microprocessors, but are just processors. So now what we have in our computers and our cell phones is we have a microprocessor, and we have several companies making this. Then what we have inside there is we have what we call memory. Memory is where we have to get the information into to be actually processed by the microprocessor. Okay. And then we got to have a entry into the computer. We call these input ports. And then we have to have an exit out of the computer. We have to have output ports. So just like people when they bust their screen up all on their phone, go out and buy a new one because it's not any good anymore. So either you screw up your input ports or you screw up your output ports or your output devices. So computers are no good unless we can do what? We can input information into them and we'll get information out of them. And microprocessors do one thing. Now, you know what these things do? They do one thing. You're the microprocessor in your phone does one thing. It runs programs, period. That's all it can do. And who writes programs? We do. Well, I have. Y'all will be. And it's a binary language. We'll look at that too. Yeah, I know. I do that all the time. And my wheelchair gets caught on things. So what we do is we have 3 buses, and we'll look at that later in a minute. We have what we call an address bus, and this is a binary bus. And what this does is we have circuitry that monitors the address bus, and this is where this guy gets it wrong. We have circuitry that's looking at the address bus, and we call these address decoders. So the mail person is an address decoder. So we're not communicating with the mail person. What do? They compare address on an envelope to an address on the side of a mailbox. So these electronic circuits with address decoders, that's all they're doing. They're just sitting there looking at the address bus, and when it sees this address come out that address bus, it's going to select one device. So the mail person only does what? One mailbox at a time. And so it's got the address decoder up here, but in actuality, the address decoder would be in here. You understand that? Now, once we select a device, we communicate. So the address bus is what we call a unidirectional bus. It's one direction. It comes out of the processor and goes out through the whole system. Once the device is selected, the communication takes place on the what? The data bus. The data bus is a bidirectional bus, which means the mail person can do what? They can put envelopes, mail into the box, or they can do what? Get mail out. Well, how does the mail person know you want them to take something out? What do? Put a flag up. Well, that's what the control bus does. So the control bus, the microprocessor sends out a signal that it's a bunch of stuff on the control bus because it's got. So we have the address bus selects, the communication takes place on the what? The data bus, and the control bus controls the communication. And one of the things it does is tells it which way to go, whether to put stuff in memory or to what? Get stuff out of the memory. That makes sense? Now, this is a CPU right here. All this would be a CPU. But in PLCs, we do what? I mean, all of this, I said that wrong. All of this is the computer. That's the CPU. All of this is the computer. But what the PLC's done is they've combined all this and they call it the CPU. We okay? By the way, this is out of my book too. No, I published a book, right, on computers. So here we go. So this is basically the makeup of a microprocessor. We have a unit in here called the arithmetic logic unit. Let me go back to the very first. Oh, here we go. It does exactly what it says it's going to do. It does what? It does arithmetic and logic. What kind of logic can we do? Anybody know logic, basic logic functions? 5 of them? Anybody? Yeah. And then plus we combine stuff. Yeah. Then we have what we call registers inside the bio, and this guy that wrote this book does an awful job on registers. He calls everything registers. Technically, the only place registers are inside the microprocessor. So a register holds the data while it's being processed. So if I was going to add two numbers together, normally we'd load it into one register and we'd load another one in the other register. We'd add them together in the ALU, and then we'd put them somewhere. Then what we have is we have what we call, so what we do, the processor is in two phases, and it's kind of blurry now because these things are very, very used to in the old days. The microprocessor was in two phases. It was either in a fetch phase or in an execute phase. Now what happens is we have what we call instructions. So I'll try to bring these up, and we can look at some of the instructions. But all these things do is they deal with a numbering system or numbers called binary. Y'all know what binary is? Yes, nothing but ones and zeros. So what we do is we have a set of codes, and I'll just throw something up here that they call them opcodes, which stands for operational code. So what happens is we put these binary codes together, and we'd have a binary pattern that would tell the processor to add these two registers. We might have a binary pattern that tells it to do what, subtract. We might have another binary pattern that we tell it what to AND two numbers together, or and all that kind of stuff. Well, what happens, this could actually be a number, but when it's in the fetch phase, whatever binary number comes into the processor goes into this guy right here. I mean, goes into this guy right here. So this guy would look at the opcode and says, okay, I'm going to do what? I'm going to add. Then it switches into the execute phase, and it does whatever the opcode told it to do. And then when it gets through with that, it switches back into the what? Fetch phase, execute. When it's in the fetch phase, it's looking for opcodes. When it's in the execute phase, it's doing what the opcode told it to do. And this is the way processor works. Now it's kind of weird because the actual time it takes, to execute instructions takes a little while, and while the processor's idle, what it'll do is it'll go out there and start prefetching information from memory. Where the instructions at? Well, they're out of memory, the memory of the computer, not a hard drive, not a flash drive. They're in the memory of the computer. And a lot of people get the two things confused. The memory would be like what you got up here, right? You understand? So this would be memory. And so what it does is it goes out and it outputs an address. And if it's in the fetch phase, it's looking for what when it comes in. It's looking for an opcode, right? When it switches to execute phase, it's switching to the what? Looking for the data, which we call operand. So what they're doing now, these processors are so smart, is they go ahead and prefetch a bunch of stuff. So used to the way it would be, the way it worked would be, I've got let's say I got 1,000 mailboxes out there, and I go outside and mailbox 0, I'd open mailbox 0, I'll bring it into the house, hand it to my wife, who's the decoder, and she'd say, "Well, Rich, you need to go out and get what's in mailbox 2, 1." And I'd go back out the door, and I'd truck out there, and I'd open mailbox 1, right, and I'd bring it back in, and I should say, "Well, this is data, and it's going to be located in mailbox 2." And I'd go outside, right? So this is the way it used to be, fetch and execute. What they do now is the control units in the processor says, while the processor's here and executing, why don't you just go out there and grab some stuff? So the way the processors now work now is that when they go out, they don't just get one address, they grab a bunch of addresses, and they bring them in and put them in cache. It separates the instructions into the instruction cache and the data in the data cache. And then it says, okay, now I don't have to go out to the mailbox, right? You understand? Because now the instruction is in what? In the cache. Now I'll do this one, the data's here, the instruction's here, data's here, the instruction, okay. Oh my goodness, I'm running out of instructions, I'm running out of data. What would it do? Well, they go back out to the memory and do what? Instead of grabbing one, it would grab a what? A lot. Bring them in and put them in what? The cache. Now eventually every program loops. Every program loops. So right now you're looking at this program and it's just constantly doing what? It's just looping. So once all the data is in the cache, it don't ever go out to the mailbox anymore unless it needs what? Unless it needs new data. So adding these caches inside the microprocessor has immensely increased the speed of processing. So you only have that short delay while it's loading in the loop, right? You understand that? And then once it's loaded, once the loop's in there, it don't go out to memory anymore. So what it does, it lets us use slow memory. This cache memory is extremely fast. And now we have some processors that have like 3 levels of cache in there, level 1, level 2, level 3. Prefetching level 3 feeds level 2, and level 2 feeds level 1, and these processors scream. These are the processors, these 2-3 gigahertz processors out there. Y'all know what gigahertz is there, right? Cycles per second. So digital waveforms use a lot of the same terms, but it's not a sine wave, it's just pulses. And then we have an internal bus. PLCs normally only have one processor. Your new computers run what they call multiple cores. Like I think mine is 4-core. I think you can get up to 8 cores in a single processor unit now, which means there's literally 8 microprocessors in there. And what it does is, if a program is written correctly, we call them hyper-threaded programs. These are programs that are written with modules that can run on their own, like spell check. So spell check could run on its own, right? So instead of me in my word processor, used to spell check was awful. I mean, you type a bunch of stuff and you never wanted to run spell check because it took so long. But now, if we got what we call a hyper-threaded application, then what this processor can do, it can assign spell check to its own core, and then your word processor is running over here, right? And every time it needs to do spell check, it's basically instantaneous now. So right now, as soon as you type a word, what happens? It's read. And if you're using Grammarly, anybody use Grammarly? That's cool. I'm just now playing around with it. It's running in its own core, but it's got to be what we call a multi-threaded application. So registers, what did it do? It holds the data. That's where the actual information that the ALU is working with. We have processors that have multiple ALUs, especially since graphics has really came into play. So most of your desktop computers have their own graphics processor. It's got their own graphics arithmetic logic unit in there. So instruction cache, all those guys do is prefetched incoming instructions. So just about now, all your processors run a cache memory. And if the processor's in here processing data, what does it do? It goes out there and prefetches all this stuff and puts it in the cache. This is actually the die of a i7 processor. These are all the caches. This is the caches down here. So this runs 3 levels of caches. How many cores does this thing had? I think this guy had, I can't remember. You can pretty much well see them. But this is actually what they call a die. So this is what they make their processor off of. This is actually the way it's set up. It's a quad-core processor. So you see every one of them. It's got the instruction recorder, floating point math unit, and then they have their own internal bus structure. Each one of them's got their what? Caches. So bus width, so address bus. What does the address bus do? I mean, it's pretty, to me, it's one of those things that just makes perfect sense to you. So what does the address bus do? Selects. So it's what the processor uses to select what it wants to communicate with. Either memory or I/O. It specifies what it wants by the control bus. So the control bus outputs one that says, okay, I'm addressing an I/O device. So you can have an I/O device at address 0, and you can have a memory device at address 0. The control bus tells it which one it's addressing. The data where the transfer takes place between the device selected by the address bus with the microprocessor. Translates data between I don't think that. The wider the data bus, the more data that we can transfer at one time. We would have to really figure out, one of the things that it's hard for us to get on the PLCs is what CPU it actually runs, or who actually makes them. We have several big companies. Most of them you probably heard of. Intel, y'all have heard of Intel, right? And of course, AMD. Those are two primary processors that we use in personal computers. Who makes these? I imagine Apple makes their own processors for your iPhone, and then of course it wouldn't surprise me if Allen Bradley didn't make their own processors for their PLCs. But every one of them's got address bus, data bus, and a control bus. The book doesn't talk about the control bus, so what does the control bus do? Controls the information, right? Controls the flow of information between the device that's selected by the address bus and the data bus is, okay, y'all got to take a 10-minute break. So the book kind of got it backwards when the guy drew the picture. The address decoders are actually on the ports, right? You understand, and on the memory. These are just electronic circuits that I could show y'all some circuits with actual address decoders. Back in the old day when everything wasn't integrated, when computers were made up of different things. So basically, this is my other little drop. So we got the microprocessor, and I drew all these mailboxes. So the address decoders will be sitting right here. Every mailbox has got an address, 0, 1, 2, 3, 4, 5. This is binary, by the way. So 0, 0, 0 would be 0, and the next one would be 1, 2, 3, 4, 5, 6, 7. So the address decoder right here is looking for all ones to come out the address bus. If all ones come out the address bus, it opens the door. And how many mailboxes can be opened at any one time? One. So technically, the processor only communicates with one thing at one time, at any one time. We call it half duplex. So here the processor is putting out this address right here. Can y'all see it? 100. This is the data bus over here. This comes out here. 100 would be this mailbox right there. And what did it do? It opened the door. Then the control bus says, I'm writing. So that tells this box to take whatever's on the data bus and store it. And then the next cycle, it would come up here. Now it's address and address. Now it's putting out address 110. Notice the mailbox door that was open is now what? Closed. This guy's address decoder says, hey, that's my address. And what does it do? It opens the box. The data bus now, the control bus says, I'm reading. So it tells the mailbox to put its ones and zeros out on the data bus, and the microprocessor reads the data bus. So the data bus is a bidirectional bus. But how does it know which direction? Well, it uses the control bus to tell it what direction. Now, there's a lot more to the control bus. There's pins on the control bus that indicates that the address is an input IO address. It indicates timing. There's a lot to the data bus, the control bus, but this is just a little feel of what the control bus does. And so, are we okay? That makes sense? Yeah. So this is some terms we need to learn. So in instructions, these are going to be commands. So what we're going to do is we're going to write programs. Programs consist of a bunch of instructions. Every instruction is telling the processor to perform a task, one task at a time. Everybody okay? So one task. And so we have a list of instructions. The list of instructions is called an instruction set. So we're going to be programming in a language called ladder. And then we got a manual out there called, RS Logic 500 instruction set. And this will tell us all the instructions that's supported by that language, but not necessarily the PLC. So this PLC supports the CPU, the processor, and this thing supports certain instructions. The application that we're using the program is called RS Logic 500. It supports all the PLCs. So what you'll do is you'll see when you look at the instruction set, the ones that this PLC don't support will be grayed out, which means you can't watch, you can't select them. So it's really neat the way this programming language is set up. It's what we call a high-level language, and we'll talk about the difference between high-level languages and low-level languages in a minute. So instruction set, what's the instruction set? It shows us the set of instructions. It shows us basically what the syntax. You know what the syntax is? Not syntax. The syntax is the correct way of writing in a language. So if you take English composition right here, not only do they grade you on the content, but they grade you on the syntax, right? If you don't punctuate right, if you misspell, so misspelling and stuff like that. The problem we have with computers is syntax has to be perfect. So if you ever learn programming languages, you got to learn the right syntax. So we'll look at our instructions, and it'll say, okay, this box has got to be this box has got to be that. And if you don't put the right information where it's supposed to go, then you're going to have what we call a syntax error. And ours is real cool. It'll let you know if you screwed up, so it won't compile over. Then we have an input port. Basically, we understand input ports now. So these are portals that allows information to flow from the outside world, right, into the what? Into the computer. And then we have an output port. The output port is what? It lets information flow from the computer to the outside world. And then we have what we call input-output ports. And these are bidirectional ports. These allow information to do what? Flow both directions. It's just like you got your USB. It's a bidirectional port, right? Because you can store stuff on the sticks, and you can also do what? Read things from them. Generically, by the way, all the ports on the computer generically referred to as IO ports, whether they fall into whatever category. So when we start looking at these ports, they're going to call them IO ports, but some are going to be input ports, right? Some of them are going to be output ports. So generically, that's what we call these things. Everybody okay? Okay. Hardware. These are the physical parts that make up a computer. You need to understand that. You'll hear that used all the time. Your hardware. So hardware, actually, if you can touch it, it's what? It's hardware. I should have put one more in here. Software. These are programs that we put in the memory of the computer that we can do what? We can change and release. And then we have what we call firmware. These are programs that's inside the computer that you used to couldn't change. Used to in the old days. If you wanted to change the firmware of the computer, you had to actually change the integrated circuits. Now we have a special type of memory that we call flash memory, where we can actually update the firmware, but it takes special applications. So every once in a while, it'll come up, and it's not your operating system, but every once in a while, I don't know about your computer, but sometimes your phone will do that. It actually upgrades the firmware on your machine. Mass storage. So people get they get the devices where we keep a lot of stuff confused with the memory of the computer. They're two different things. So if you got a USB thumb drive, that is not memory, even though some people call it, it's what we call mass storage. So memory is just what you got in here. A mass storage device would be the way we use books. So what do we use books for? To hold information until we can load it into our memory and process it. All these USB thumb drives, solid state disk drives, hard disk drives, these are all what? These are mass storage devices. Even though some people call them memory, it's just that they don't know it. So where's the memory of the computer? It's inside the computer, right? Understand? You know the difference. So if somebody is your boss calls thumb drive's memory, you go along with it. If somebody is supposed to know the difference, you correct them, right? If it's not your boss. We hear that. I got 10 terabytes worth of memory. No, you don't have that much memory. There's no computer out there that can address that much memory, right? You understand? What are they talking about? They're talking about they're starting a mass storage device, like their solid state disk or their hard drives or whatever it is. We have two types of computer instruction sets out there. We have what we call, used to be when we first got into computers and doing what we call binary language, which what we call machine language, is to do very complex tasks. We would have to have multiple instructions to do very complex tasks. Well, over time, what happened, we were doing all these instructions all the time. So over time, we said, well, why don't we just combine this whole thing into a single instruction? And so what it did is it reduced the number of instructions that were available, which made programming the processor a lot easy. We refer to these as RISC processors. So just about all our processors are now what we call RISC processors. So complex instruction set computers, right, or reduced instruction set computers. So that's what RISC consists of. And I don't even know why they brought it up. That's something that we don't need to know. But that's important. So this is important. Memory devices, basically the memory in the computer is split into two main categories. We have what we call random access memory, and this is the read-write memory in the computer. So this is where you can put information into it, or you can do what? You can get it out. So when you load programs into the memory of your computer, you're loading them into RAM. And then when you get through with them, you can dump them out. You can load another one into it, right? You can sit there on your word processor. You can type stuff on there. It's being put in RAM, which means it's what? It's read-write memory. And then we have what we call read-only memory. So RAM holds software. Software programs that you can do what? You can change. Mass storage devices hold software. So we can delete programs on our mass storage device. If we can load in, if we understand them, we can load them in. We can change them around, right? You understand that? Firmware, a type of programs in the ROM, it's called firmware. Firmware is like your operating system. So you have your operating system is in your memory, right? You understand? And this is what's controlling your breath. This is what's controlling your eyes. That's your firmware. But then you have RAM in there. RAM is where we call it short-term memory, where you do what? You bring stuff in, you process it, and then you do what? Kick it out. I'm bad with names because I've got so much garbage in my brain. If I don't think I'm going to see you again, this is true. You can give me your name, I can shake your hand, and by the time I let go, I forgot who you are. Because it's in my what? It's in my short-term memory, right? And that's basically where there's certain information we put in the firmware. Now, used to, firmware was the only way you could change the firmware in a computer was to change ICs, change integrated circuits. But now we have a type of memory called flash memory, and they call it flashing the ROMs. Very critical. If your computer ever asks you to do that, don't ever turn it off, right? And hope your power don't fail. Because what happens is you screw up your firmware. That would be like a surgeon getting in your brain and messing up your firmware, right? So, not good. So static memory, this is what your cache is made out of. Static memory is it's really fast. It takes up a lot of space. So transistors, which are our main electronic device that we use to manipulate data, It takes in static memory, it takes 5 transistors per every bit of memory to hold either a 1 or a 0. But it's extremely fast. So your cache memory is SRAM. You don't see that. But what they did, since the cache memory came out, it allowed us to use this slower stuff, dynamic random access memory. So this is usually the main memory in your computer. Somebody says I've got 8 gigabytes of memory. It's usually dynamic memory. And what this does, it uses a little device called a capacitor to store bits in 1s and 0s in. And it takes 1 transistor per cell. So it means automatically I can get 6 times the number of storage, DRAM storage that I can for 1 static cell. So static cells, they don't have to be refreshed. The problem with DRAM is that it acts like a little tiny battery. And what happens to batteries? They discharge, right? So what we have to do with the dynamic memory is we have to refresh it. Used to, we would do it with a program. All you have to do is just go out and access it. That's all you have to do. And it would restart itself. But since dynamic memory's been around so long, now the support chips actually control the refresh. But the problem is, while it's refreshing, you can't be using it, right? You understand? So DRAM is a lot slower. But now that we have all this cache memory in there, then it makes it a lot. It compensates for it. That makes sense? By the way, memory in computers, we call it DDR. I think we're on DDR4. That's not, it's synchronous. Double data rate, synchronous, which means it transfers on 2 cycles, dynamic random access memory. So if you go out to memory, if you got a desktop and upgrade the memory in it, you buy what they call DDR now, which is dynamic memory. SRAM remains unchanged until SRAM, which the memory in your computer, except for your firmware, RAM is what we call volatile. Anybody know what that term is? Volatile memory. That's exactly right. So all volatile memory in your computer, everything's gone as soon as you turn power off. So this is why we have to boot our computer every time, because the operating system is in RAM, right? It's in a volatile memory. If it's not in a volatile memory, it means you would have to boot your computer. You turn your computer on, it would do what? And it would do what? So your operating system here is in a non-volatile memory, which is pretty neat, right? That makes sense. But they're still ramming this, but these guys stay on all the time. You understand it? So you don't ever turn these things off. In the old days, if you wanted nobody to get to you, what could you do? You could pop the battery out, but just now, just about all the time now, these things are never turned off. So if the battery dies on these, you're just messed up. So SRAM and DRAM is volatile memory. Firmware is non-volatile. Volatile means if you turn it off and remove power from it, everything's gone. It's just gone, huh? Yeah. Everything in RAM is gone. Huh? No, everything's in RAM. In fact, if I've got a hard drive and I load a program, it loads it into the RAM of the machine. And then the microprocessor fetches information out of the RAM. And it goes through the cache, which compensates for the DRAM. But the RAM in the machine is volatile. It means every time you turn the computer off, it's what? It's gone. So I'll come up here, I'll turn this sucker off, and then when I turn it back on, I gotta wait for it to go out to my mass storage device, from the ROM. So there's a program in the firmware that causes it to go out to the mass storage device and loads my operating system into what? Into RAM. So the operating system on this computer is running out of RAM. Now, if you got a tablet, those things are never off, right? You understand? Their batteries will run down. So if I turn this sucker here off and I turn it back on, the state of the battery is going to be exactly where it was. If I come over here right now, this thing thinks it's off. What's happening to the battery right now? It's running down because it's what? It's never off, right? Never off. If it goes off, you're going to lose your operating system. I mean, if the battery on this thing ever fails, then by George, it's gone. Everything you've got is gone because it's stored in RAM, right? And it's a volatile memory, which means what? If you back it up if you plug it in and you back it up to, using iTunes or whatever, I don't know what the Android uses, it's stored out there, and then you can restore it, right? You understand? It's just like if I backed up this computer on a mass storage device like a USB hard drive, and it totally crashed on me, then I could do what? I could restore it and get it back. I understand that. RAM is what we call volatile memory, which means if it loses its power, everything in there is gone. Does that make sense? So this is why the computer has to have ROMs on it. ROMs are non-volatile memory. And what we put in ROM is there's what we call a basic input-output system. And every time you start your computer up, what it does, it goes to a certain address inside the ROM looking for the first instruction. So this is like what we call our, what do we call it? Automated nervous system. So when you're born, you already have an operating system. So that's what we call, this is stored in your ROMs, right? You understand? Non-volatile. It's always there unless a surgeon gets up there and screws around with it, right? Always there. So when you're born, what can you already do? You can already breathe, right? You can get rid of, right? Get rid of waste, right? Yeah, you breathe, right? Your heart works, right? So this is what we put in ROM. We put what is called a BIOS. It's called a basic input-output system. When you apply power to that thing, the first thing it does is goes to an address in the ROM looking for an instruction. And then after that, it's under control. And so these guys, what you do is it'll run through most computers run through what we call a power on self-test. So when you turn your PLC on, you'll notice the lights blinking. And what it's doing is just going out and checking to see if it's okay. And then what it does, it goes into ROM and does what? Loads. It might the whole operating system might be in the ROM. So here the operating system's in these things. On these things, what it does, it has what they call a basic input-output system, which means the operating system, the main operating system's not in there. So this guy right's got Windows 7 in it. Now, what am I fixing to do to it? Now, how can I do that? Well, the operating system's not in ROM. No, I don't. I can get a DVD. We've got Windows 10 on it. Do an upgrade. Go out there, get a new operating system. Because these computers, the operating system is not in the ROM. The operating system is ran out of RAM. So that's why these computers have to go what we call a boot sequence. So you turn it on, it goes up into ROM, starts the little power on self-test, does some other things, initializes all the programmable chips, and then goes out looking for the operating system on a mass storage device. Loads that into RAM, and then it turns control of that over to the operating system. These guys, the operating systems are there. So on these guys, the entire operating system is inside the ROMs. And what do you think the operating system does? Well, a computer, only thing it can do one thing. A microprocessor can do one thing. What does it do? Run programs. And when you reset it, it always goes to the same address, looking for an instruction. And that first instruction is going to be in ROM, right? You understand? And then after that, guys, that's the only thing it does on its own. It goes to the same address every time you start it up. So when I plug this sucker in, it goes to the same address every time in ROM and starts running what? Starts running the program. And then it's under the control of the program. A microprocessor does one thing. What does it do? Run programs. And so our programs are going to be stored in a non-volatile memory inside here. So we have mass ROMs, which we don't see much anymore. So mass ROMs, if you change the firmware, you had to actually change the integrated circuit. So what happens, and that's the way we would do it. I mean, so if your computer, if they needed to update the BIOS, you just have to go out and buy a new computer. Then they came out with what they call programmable read-only memory, which stands for PROMs. These guys, they actually had fuses inside of them. And what you'd do is you'd put it in, like this guy, y'all see it over there? Put the PROM programmer over there, brown box over there. It's got a socket on it called a zip socket that we'd put the IC in there and we'd lock it down. And then we'd run an application on a program and we'd store what we wanted to in it. And it was all ones and zeros. But what it would do, when you stored it, it would actually blow fuses for every place you wanted a 1. And it would leave the fuse for every place you wanted a 0. So I mean, once you've blown a fuse, it's what? It's blown, right? You understand that? So those guys were one-shot deals, which means you programmed them, and if you wanted to reprogram, you'd take that out and you'd throw it away, and you'd put another one in there. So that's why we hook a computer up to it so we could save the programs in there. Then we went to erasable programmable read-only memory. These guys right here. So these are ROMs. But these are EPROMs. Still very, very popular. What we can do with these is we can erase them by exposing them to high intensity ultraviolet light. So that's why you see that glass window in them. So we'd have a special thing we call an EPROM eraser, which is nothing but a fluorescent light without all the filtering on it. You'd slide it in there and it erase it in 30 minutes. You could put it outside in the sunlight, and it would take about 2 or 3 days for the sun to erase it. But you could erase them outside. And then once you erase them, then you can put them in the programmer and do what? Program them. So these are very popular for a long time. And to keep them from getting exposed to light, what they do is they'd take an opaque label and just write what was on them. And you can see that one where they still got the label on them. So that way, if they got exposed to any ultraviolet light accidentally, you wouldn't erase them. The last one is what we're using now. What's it called? Double EPROM. Some people call it E-square. This is electrically erasable, programmable, read-only memory. This has changed things. So just like every computer now has. And we use them. We just don't use them. We use them. We use them around, but they're not. Your USB thumb drives, these are nothing but double EPROMs. Which means we can do what? If we got the special equipment inside that little stick, we can. If we got the special circuitry, we can go out and erase them and then rewrite them. You ever notice that it takes a lot longer to write stuff to your USB than it does to get stuff off of it? Because it's having to do what? Erase and then reprogram. Erase and then reprogram. When you read, it just reads. So now our ROMs, just about all the double EPROMs. These are non-volatile. They have a circuit built into them. If they need to upgrade the ROMs, they'll let us know. These are not easy, but these probably use either PROMs or regular ROMs. But the new compact logic that they got out, you can flash the ROM, but you got to do it through Allen Bradley. It's not easy because they don't want to make it easy, because if you wipe out your firmware, you wiped out your basic operating system and now your computer's dead, right? So normally, if you're going to, and that's what they call it. They call it flashing. You need to flash your ROMs. You need to flash it. This computer right here does it. Right now it says you need to upgrade your firmware. And it says do not unplug. Keep connected to it. Says use a hardwired Ethernet. They don't even want you to, you can't even flash them if you don't have it connected to a hardwired Ethernet. So this computer, this Lenovo, I don't know how many times it's updated the firmware on this one because it's using what? It's using these double EEPROMs right here. So, but you have to have special circuits inside the computer, and then you have to flash them with a special application, which Allen Bradley does not give you. Y'all understand why, right? Because if they gave it to you, then what could you do? You could wipe out your automated nervous system, which means all of a sudden, if they did that, you'd be dead, right? So usually most of the flashing is done through the maker of the computer. You usually have to be connected to the internet. This one I've never seen this request that, but the Compact Logics do that every once in a while, which are the new PLCs that Allen Bradley puts out. So those are read-only memories, right? Everybody understand those? You okay? Basic input-output system, we already talked about this. On PowerUp, the firmware or the software is in ROM. I don't know why it says that. Carries out several instructions that checks the input-output. So when you turn these PLCs on, you'll see these little old lights up here flash. We call it a power on self-test, or some people call it a POST, which is an acronym. It's not after. So that's when it's running its little self-test. And then once it passes, if it don't pass, then the red light will stay on. It'll start blinking. And hopefully it's up enough so you can go in and read the status table with it. If it don't, then you're just messed up. Then you'd probably go on the internet and look at, we used to call them beep codes. If the old IBM PCs, the compatibles, failed the power on self-test, it had an internal speaker to start beeping at you. Beep, beep, beep. It'd be short. It's kind of like Morse code. And you could look it up, and it would tell you what on the keyboard, what had failed and stuff like that, which is pretty cool. Now I don't do that anymore, and I really miss that, guys. Because what it would do is if it passed the post, it would beep once. So if you've heard that one beep, that was the best thing. If it didn't hear that one beep, you know it failed the post somewhere. Address decoders, we've talked a little bit about that, right? Monitors address bus and enables the address device to place data on the data bus. It's either going to read or write. Support chips in personal computers, we call it a chipset. Like I said, when we first got into computers, I could bring a motherboard over here and it's got hundreds of chips on there, but they always did the same thing. So what they did over time, they took all these chips and integrated them onto a single thing, and now we usually call them chipsets. So normally if you look at a motherboard, you'll see a microprocessor, and down below that you'll see a big old integrated circuit below that actually runs the motherboard. But these are all the support chips. This is sort of what a power supply looks like. We really don't need to understand that. We're not going to troubleshoot. But what does the power supply do? So this guy here operates off of what? DC. I plug it into AC. So it's got a power supply built inside of it, and what does it do? It converts to what? AC to DC. If you take solid state, we'll get into power supplies in pretty good detail. And here all we need to know is what it does, because we can't fix the power supply anyway, right? You understand? Right now, it probably cost more for a technician to fix it than it would to do what? Replace it, yeah. That's what computers are now. These are our input ports. First of all, so this would be an AC input port. So what these guys do right here, and this is different than the book because the book is not quite right. They leave out some resistors that if they wasn't in there, they would burn in. So what happens is it lets current flow against the arrow. So in any one time, if I put a negative and positive right here, then this current would go here. It flows against the arrow. It would come here, right? That makes sense? Then what it would do, it would go out in this direction. It would come up here. It would go through this. Then it would come back through this. and it draws against the arrow, so it'd go this way. Now, if I come up here and swap polarities, what you would notice is the current flow through the external circuit is the same. So I had the minus on top, right? So if I put the minus down here and the plus right there, it would flow through this resistor that's in there for protection. It wouldn't go that way. Why? Because it's against the arrow, right? It'd go this way. Wouldn't go that way because it's against the arrow. It'd go this way. And it goes through what? Same direction. Comes through this, comes back. Now what it's doing, it wouldn't go through this one because this is where it came from. I mean, it wouldn't go from this one because this is where it came from. So it'd come back this and go back to the positive. So that's the rectifier. This is what's in your car. It takes the AC off your car. This is make sure we have a certain voltage. This is called an optical isolator or optical coupler. The problem is over here, we might have 120 volts AC, and we got all this electromagnetic interference over here. We got all this garbage over here. Over here we have plus 5 volts. So what we need to do is we need to have the ability to couple the input signal into the computer and make it totally isolated. What we do, this is a little light emitting diode. You know what a light emitting diode is? This is what we call a photo transistor. So what we're doing is we're passing information from the actual input port into the PLC using light. It's just like the remote on your TV. So you change your channel to light on the right. We'll pick it up. I'll try to do something on my remote. It's not going to do anything. Y'all see anything? Okay, so I'm trying to pass you information. And this is what the optical coupler does. So what we're doing is I'm completely different from you, but I can pass information from you, right? You understand? And we're totally isolated from each other. See it blinking? So it blinks, whatever rate it blinks at, that's what's telling the projector what to do. So I can do different functions, and it would blink a different pattern. It's doing it faster than y'all can see it. So that's what an optical isolator does. So it actually isolates me from what? From you, and I'm passing information. So I'm not touching that camera, that projector up there, but I'm able to pass information through it, and we're isolated from each other. So what it does, all this garbage that's in the outside world, we can filter that out, take DC, convert AC, convert it to DC, have 120 volts over here, 5 volts over here, because we're coupling the information through this optical isolator. That makes sense? And this is on all of them. Not only is it on the input ports, it's also on the output ports. So this guy right here, reflect, burn up. It's the way it's. This is the one that's in the book. This guy doesn't understand. We can't put this guy directly across the input like that. But this is still a pretty good deal because he does about the same thing. So what it does, it lets us take an environment over here that might be DC, it might be AC, it might be different things. It might be 24 volts, might be 120 volts, and we still couple it into the PLC, and we get 5 volts on the other side, right? Everybody understand that? So there's optical isolator. This is usually the guy that gets burned up right there is optical isolator. So that's why it's nicer to have more input ports than you need, because if you mess up one, you can do what? Move to another. If you got an extra one, but then you'll have to rewrite your program. So these are, I went and got these off the internet because I knew the one in the book wasn't exactly right. But you can understand, even though it's not exactly right, we understand what those optical isolators are for. I don't know what my computer's doing. So it talks about an octal latch. I don't know what he's talking about there. So don't worry about that guy. Now outputs are a little different. So notice on our outputs. So here we have information from the computer, and it's sitting at what? Plus 5 volts. What this does, it fires this device called a triac. A triac is an electron. I don't know why it keeps jumping on me, guys. A triac is a device that makes it. So what we're doing, and the book left this out, by the way, the triac does not produce power. It just controls what's there. So what I added to my slide, good gracious, I know what's happened. My touch screen is turned back on. This is input, this is input, this is input, this is input, okay, this is output. So what we do is we have a AC source out here, and when the SCR is turned on, it allows current to flow through it AC. So a triac is a semiconductor device that we can it acts like a relay contact, but it's not. So when we turn this guy here on, it passes it through. When it turns it off, when we turn it off, it stops the current flow. That makes sense? So what we're doing though, we're still coupling through a what? Optical isolator. So over here we've got plus 5 volts. Over here we're controlling whatever this is. Could be 120 volts, which is still pretty popular in motor controls. So what they left out in the book is the actual source for the power. So the book does not have a blue circle with AC. So that's an AC power source. Are we okay? So a triac output, which means, so what I do is I can turn on an output. And what can the load be? What kind of loads did we go through the other day? Light, could be a light. So I could output turn on a light with an output of my PLC. What else? Could be a solenoid, right? Could be a relay. So I could output this and control a relay, which could give us what can relays do for us? I can do that with a light switch. Well, what does relays do for us? It's a magnetically controlled switch, but what can we control with a relay, with the coil of a relay? We can control AC, we can control DC. So the contacts on the relay, the voltage controlling the coil and the voltage across the contacts do not have to be the same, right? You understand that? It's just like you and that light, that what you're switching over there are not the same thing, right? I can go over there and switch it, or you can go over there and switch it, right? You understand? That switch could be controlled. The contacts on that switch, my God rest him, he was a good guy, but my sister's father-in-law, he was a carpenter, and we went over to his house one day, and he had his lawnmower. And the light switch and the key had gone out on his, where it didn't start his motor, and he wired up a light switch out there. So he had a regular light switch on his ride lawnmower, but he would use it to crank the thing. Of course, he had to turn it back off, but it was a regular light switch from Lowe's, because the light switch don't care if it's controlling what, DC or AC, even though we do. It's just a switch. So you go out there and you move it, it closes a contact. Well, what can be across those contacts? Well, it can be DC, it can be AC, it could be 12 volts, which is what that system was. It could be 120 volts. You just don't want to exceed the rating of the switch, right? You understand that? So that load out there, what we're talking about, it would be a relay coil. It could be a relay coil. And then over here, I'm going to be controlling contacts. And what could be across those contacts? Anything, right? But the coil would have to be an AC coil. So that would have to be an AC coil. Couldn't be a DC coil. So you couldn't take a relay out of your car and hook it on the output of a track because it'd burn it up, right? That makes sense? Yes, no? Yes, no? This is the top one. This is a DC output. It's what we call a sourcing output. This is an AC output, the one we just looked at. And then this right here would be what we call a relay output. So what we do is we take the output of the optical isolator, which we didn't have that, so this would be over here. And then that picks up a relay. And what advantage does a relay output have over a DC output or a TRIAC output? This could be what? Could be AC. So a TRIAC output controls AC. A transistor output controls DC. A relay output, you can do what? Either or. So this guy right here has relay outputs on it. Your 1000 has relay. So this guy's controlling DC. The relay outputs on this is controlling DC. Yours, that one is controlling 120 volts AC because they have relay outputs on it. Some AC outputs will also use 0 volt. We don't do that. So these are the three types of outputs you can have. You can have transistor outputs for what? DC. You can have TRIAC outputs, which are what? AC. Or you can have relay outputs, which are both. So what would be the disadvantage of a relay output? Y'all remember the disadvantage of relays? The biggest disadvantage of a relay output is speed. They just don't switch fast. So if you're using a pulse train output or you're using what we call pulse width modulation, pulse width modulation, you would never run that on one of these guys because it just can't do what? Can't switch fast enough. So if you got one of these running like a variable speed drive, variable frequency AC drive, no way an AC output could do that because that's what it does. It uses what we call pulse width modulation. Now we'll talk about this. I know it's time for another break. We'll talk about this. Let's say sourcing. That's something we're going to have to understand. And the book only touches on it, but it's something you're really going to have to understand. In fact, one of the guys he interviewed at Toyota, and guess what he asked him? Did he know the difference between sinking and sourcing? And he said, yes. So, all right, guys, y'all take a 10-minute break. So octolatch, this guy don't make any sense about that, so y'all don't worry about that in the book. The three types of outputs, we need to really know that because we buy the PLC. One of the things we specify is outputs. So if I came up here and looked at these outputs, if I looked at the module, it says they are sinking. The input that says the sinking, and the output says they're sourcing. So we need to understand what that means. Did y'all see that? We know that. You did? Yeah, so if you look at the inputs right here. So if you look at the inputs right here, it says DC sync and it says DC source. So that's our guy right here is a sourcing output. Which means but we'll have to look at we'll have to learn. So common in PLCs means something a little different. So if you got a PLC that has an analog input, what does it do? Inside it's got a special thing called an analog to digital converter, which basically converts an analog signal into a binary number. So these PLCs have two analog inputs. They allow inputs from 0 to 10 volts. It can be anywhere between that. And it's got a 10-bit A to D converter, so it's going to take that and split it into 1,024 different binary numbers. So 0 is an example. If it put in a 0, the number would be 0. If it put in 10 volts, it would be 1,023. So 0 counts as one of the numbers. 1,023, and any range between that would be a number, but it would be a binary number between what? 0 and 1,023. Because it's 10 bits. A digital, the analog converter would do the same thing. So if it had a 10-bit, if it had a 0 to 10 volts, by the way, is very common for analog inputs and analog outputs on PLCs. Very common. So on the analog output, it would put a binary number in there from 0 to 1,023. So that's the number of combinations. So actually, what it would split it up to is 0 to 1,023. So if the PLC stored into the digital analog converter, if it stored the binary number equal to 1,023, then the DA converter would have 10 volts. If it stored a 0 out there, it would store what? It would put out 0 volts in any number, but if it takes 10 volts and put it into 1,023 volts, it shows. The little 1200 PLC right here has got a 12-bit. So this has got a 12-bit AD converter in it. So it's got two analog inputs. It has the 4,096, 0 to 4,095 different counts it could divide it into. So the more bits they use, the more it would be true analog, right? Does that make sense? I'll let y'all look at this scope and y'all can see the analog to digital converter, and you can actually see the steps. Programmable logic controllers are used to implement specific instructions. So we have what? We have timing instructions, output instructions, timing instructions, counting instructions, adding installation instructions. Ours, in this semester, we'll get through the first three. In advanced PLCs, we'll get through the rest of them. Here we got to get all this basic stuff out of the way. That's why we can get through more than in advanced PLCs, because in advanced PLCs all we're talking about is instructions. And this one we got to learn how the computer basically works before we can get into the instructions. So this is why we can only get through counters and timers. So all ours is going to be in here. The first three. And these are usually the categories that the PLC is going to support. Does this make sense? Okay. Programming. First of all, to get into programming, we're going to have to learn a computer language. So originally, the language, and I think I've got this in there, I got this in book. But originally, I was learn how to program. We get to language. We got nothing but you got to know everything about the processor. You got to know the registers. You got to know the names of the registers. You got to know what they would do, how to manipulate data. It's a very, very complex language. And then we'll show you all an assembly language. So binary language or machine language is we don't do that for what's nice about our language, pictorial type language. We don't have to come up with the instructions. We're going to pick from a palette of instructions, and we're going to pull them into our program. If you took anybody had intro robotics, and you play around with the Mindstorm, that's what you do. You have a palette of instructions, and you pull instructions into a program. That's basically the way of a program. Source code. So the only language the microprocessor understands is this language right here, and that is a complex language. Then they came out with a language called assembly language, and then they have what we call high-level language. Well, any language that's written in any level of language that's not machine code, the actual code is the source code. Do y'all know what a driver is? That's a good place to be. Y'all know what a driver is? We need to load the driver. You probably need to install the software. What we have, that's the name of it. But what is the only thing that microprocessor can do is run what? Programs. So this drive has a program that makes it work. You just let the program that makes it work. You just get a program that makes it work. So these programs that are written to support a we call those drivers. Because an operating system is nothing but thousands of drivers. So everything out there has to be controlled by a program. Everything. So to read information off your USB drive, it has to do what? It has to run a program. So every once in a while, you plug a new device in there, and it don't have the driver, and it asks you to do what? Now, you go out and buy a new printer. It comes with a what? A disk to load the what? Driver. You know what's not. You can do what? Copy that driver to it. So a driver is what? That operates a piece of software. And then what we do is we have something that allows us to control all those drivers. We call it. So Windows Explorer, that's a shell. It's what we call graphical user interface. You had to type everything in. It was a text shell. And you still have to call command prompt. If you're in network and you have to learn command prompt, you have to use command prompt. It's still out there. So when we got there, the operating system that we sized up. Y'all know where y'all can get the command prompt? And they still support it because of networking, right? You understand that? I might have it on my desktop. Command prompt. So this is what our operating system used to look like. If it comes in. Come on. It was just a, here it is. This is it. This is what we saw. So the whole screen looked like this. And this was command prompt. And what we had to do is we had to type our commands in. So if I wanted to copy files, I had to type in a command to make it copy, say where to come from, where to put it at. If I wanted to delete files, I'd have to type in a command for delete. If I wanted to run a program, I'd have to know the name of the program to run. And this is command prompt right here. And it's still available because it's still a lot of your commands to control Ethernet. We call it the TCP/IP protocol suite. You ever heard of that? Well, that's Ethernet. That is Ethernet. Y'all have heard of Wi-Fi, right? Ethernet. Well, it runs a protocol called TCP/IP, which is a transfer control. It's a transfer control, the TCP, transfer control protocol. And that's the way it puts packets together that it transmits. So when you transmit data, you're not on the network all the time. You transmit one packet, and then you come off the network, and you check to see if anybody else is on there, and if not, you send another packet. And then it's got IP. IP is the way we address the computers. Y'all have heard of IP addresses, right? So that's the way we address the computers on a TCP/IP network. We address it by an IP address, but the packets are assembled according to a TCP protocol. Well, this guy right here allows you to control that. You can trace the circuit. You can actually see. You can use a trace circuit command, and you can actually see how it goes to get to where you're going to, the actual routes it has to go through. You can reassign IP addresses. You can release IP addresses. You can see the IP addresses of everything on your computer. It's called IP config. And then /all is going to show you everything. So what this is going to do is this is going to show me all the different interfaces on our computer and what IP addresses they have. And there they are. MAC addresses, which I don't understand. So the MAC address is actually the physical address. Can y'all see that? 3C970E8661F3. That's what we call the MAC address. It's a medium access control. What that is, that's the physical address that's built into your network cards. Those are put in there by the manufacturer. And then an IP address is what we call a logical address, which means they can change, right? It's assigned by software. So everything, your cell phone has a MAC address. Most of the time you can go to your cell phone and go to information, it'll show you the MAC address of your Wi-Fi, because you do the Ethernet. Ethernet, you're using Wi-Fi, which is basically just, it's implementing Ethernet over the airways. So this is what we used to be. So right now we had this little blinking line down here. If it's down here at the bottom, see it blinking? Can you see it blinking? We call that a cursor, because that's what we wanted to do sometime. And that was true, because you had to learn everything. Not only did you have to learn the commands, but you had to learn the syntax for the commands. If you use the wrong commands, you could literally wipe out a whole disk. So we could do a lot of neat stuff with these. Fortunately, they don't support debug anymore. That's the shell, but now we use what we call a GUI shell, which is a graphical user interface. So if I want to copy files, what do? I can drag them, I can drop them. So it's made a lot of difference. But we're going from a computer that could do almost everything, and it had 640K of memory in it because everything was text. Graphics takes up thousands of bytes of memory, thousands. So what's happened and why our operating systems and why our computer has to have so much memory in it is because of what? Because of GUI interfaces. So. Machine language. So luckily we don't have to know this anymore. The only language the microprocessor understands, all other languages have to be translated. So by the time it hits that microprocessor, it is machine language, ones and zeros. It's a binary language. We talked about operational codes, right? Programmers must know the microprocessor registers, must know the capabilities, must know the instruction syntax, must know all the addresses out throughout the program. You have to know how to access the driver for the video. You have to know all the addressing modes. We'll talk about addressing modes not in this semester, but if you take how we access the data, you have to know everything. So this is an example of machine language. This is actually dumped out of memory on a computer. We used to dump this out, but they did away with, we used to have a program called debug, where we could literally dump the memory of the computer and we could change it. We figured out where they put all the error messages that would pop up on the screen when you did things stupid. And we actually went in there and changed them. So that instead of saying, make a mistake, we'd say, you really screwed up this time, and stuff like that. We actually figured that out, but it was very complicated. This is machine language, guys. Assembly language. Assembly language uses mnemonics to represent instructions translated into machine language by a machine language program called an assembler. And it's called instruction list programming, which is on for PLCs. So we can actually program PLCs in 5 different languages. And one of them is called instruction list, and it's basically assembly. So what we do is, even though it's still complex, it's easier than machine language programmers, you still need to know everything. So this is the same program written in assembly. So move AX into address 021 hex. AX is one of the registers. So these are the registers names, AXD, XXX. So move, add, but basically now it makes a little more sense, right? You understand? So it would be a lot easier to learn how to program assembly than it would be able to program machine language. But the microprocessor cannot run this. So what would we have to do? Well, we'd run it through a translator we call it an assembler. Follow me so far. High-level languages, this is what we're going to deal with. Written using terms and expressions common in the English language, does not require knowledge of the microprocessor address and modes. We translate it by either an interpreter or a compiler. Some high-level languages we use PLCs. We're going to use ladder. This is the one we're going to use. And basically, it's going to be, we're going to draw ladder diagrams. We're going to pull instructions down from boxes. We got a palette up there. If we want to put a normally open contact, we pull down from normally open contact a picture. This is the predominant language. Probably over 95% of the languages of programs for PLCs is written this language right here. Structured text, I don't have an instruction list. Function block, this is basically function block. Sequential flow charting, this is basically like a flow chart that we used to do. I don't know if I got any examples of these. I got some for this is the language I first learned a high-level language called BASIC. Beginner's All-Purpose Symbolic Instruction Code. So that's an acronym. But it's English. So CLS would clear the screen. So whatever I want to do would clear the screen. Input means I want to get something from the input from my keyboard. I'm going to display on how old are you today, and then I'm going to put that in a variable called age. I run the program. All you'd see pop up would be how old are you today? And then it'd have a little bunch of cursor out there, and you type it in. Then it would do the math. You'd never see that, and print would cause something to go up to the display. But I don't need to know the microprocessor. I don't need to know how many I/O devices it's got. I don't need to know anything. All I need to do is know how to write this program. And then what I do is to run it, it has to be what? Translated. That make sense? Okay. And what a translator does, it takes this high-level language and converts it over to machine language for the processor. Not this one. We're going to learn ladder. It's a lot easier. So ladder. So just to give y'all a feel of it, so I'm going to come up here and we're going to use RS Logic 500, which is, I'm going to show y'all RS Logic 5000 and let you see just right off the bat is that how easy it is once you learn one ladder language. It's very easy to move between processors. So this is RS Logic. This is what we got. And I'm going to come up here and I'm going to say I got a new. First thing it's going to ask me, okay, what CPU do you have? Because every CPU has a different language, and it's got to know how to do what? Translate it. So I'm going to use the MicroLogic 1100B. It's written on the side right here. Here we go. This is a rung. It's rung 0. Well, I can't put anything rung 0. This tells it to loop. So I'm going to come up here. There's a rung. I want to insert a rung. There's a rung. Huh? Yeah, so it automatically keeps 0 at the top. Yeah, I want a contact. So I'm going to come up here and there's a symbol for a contact. I'm going to drive it in. I'm going to put it there. I want a examine if open, put it there. I just drag it in. It'll turn green where it's legal to put it at. I want a relay coil or a simulated coil. I put it right there. Now what I've got to do is I've got to assign them addresses. Identify which input am I going to get this information. This is ladder language. Very similar to relay logic, right? Got two rungs, L1, L2. Input devices are between L1 and the load. And we only have outputs. All we can do is control outputs. What you connect to the output can be anything. So here I don't have symbols. I don't have to know symbols for limit switches. I don't have to know symbols for anything. All I got to know is what I have attached to the input. So I'm going to come over here and I'm going to say input 0/0. Well, what I did, and I'm going to give it a name. And we'll talk about the importance of this. And so what I've done this, I've assigned that to whatever I hook up to input 0. Whatever I hook up, whether it's a push button, it don't care. We assign it to a port, and that's how easy it is. I could assign this to an output. If I'm going to assign this to an output, I start off with O, which means what? Output. And then I would say like 0/0 because it's a different device. And so what I've done, I've assigned this rung to this output right here. Okay. And then we got to assign these things. And I'm going to assign this to input. I don't have my PLC hooked up. I'd download it into the PLC. But this would have to be what? This would have to be a different address, right? You understand that? So input, and I'd say :0/1. And what I've just did is I've assigned this to the one called 1 up here. So this is assigned to the input label 0. The second one is assigning it to input 1. What do I hook up to that? Well, any input. It could be a push button. It could be a sensor. It could be anything. All it says, okay, if that input is true, then that simulated contact would close. These are not contacts. These are all simulated, right? Does that make sense? And we'll assign them a name. Here they call them symbols. On newer PLCs, they call them tags. So on RSLogic 500, these symbols are optional. Your new programs require you to assign names. And we'll show you why. I'm going to see if I got an error. So right now it says it don't know if it's right or wrong. So I'm going to come up here and I'm going to check the syntax. I'm going to click on this little thing right there, and the error disappears. So I know the syntax is right. It don't mean your ports are right, but it means the syntax for the instruction is right. Huh? This little computer sign right here says check the program. That's all it is. We're going down. We got another computer lab with PLCs hooked up to them. Yeah, the computer lab, by the way, is room 200. We'll see that the first lab we'll do is a lab that is a program that I wrote, where lets you practice converting number system. I want to insert another rung. I'm going to come over and click on this one. I'm going to slap it. And you can move it. So I wanted it to be right there. Look, I can grab it. Y'all know how to drag, right? So I'm holding it down. I'm going to move that rung right there. It says it's got an error. Why does it got an error? Well, it don't have any inputs. It don't have any outputs. So right now it considers this to be a short circuit. And then I'll come up here. And these are all our palettes, so we'll get through this far. Timers, counters. You know, if I wanted to put an on delay counter, I bring it down. All I do is do what? All I do is just drag it down. I come down and I drag it down, and it shows me where it'll go. And now it's waiting for stuff. Y'all see the blocks up there? It's got the black line on there. It's waiting on me to enter stuff. So I got to know what I'm supposed to enter. And that's what we'll learn. But this programming in ladder line, and this is, I could bring up TIA Portal, and it would be the same. I could bring up RSLogic 5000, it would be the same. We do the same thing. We have an instruction palette. TIA Portal palet's on the right-hand side. I don't really like this because you got all these instructions, and you can only see one tab at a time, and you have to do what? You have to keep going. The TIA Portal, all your instruction palette is in a window on the side, and you got access to them real fast. So it's got little advantages. But this is ladder language, guys. And it's a high-level language. This computer has no idea how to run this program. So what do I got to do? I got to run it through a program that translates it, right? And of course, the translators are written right here. Here they just call it. So I'd come right here, and I'd click download. When I download it, what's it going to do? It's going to translate it. And what this guy does, it don't see the high-level language. It sees the binary program after it's been translated. So the binary program goes to the network cable, comes over here, and it stores it in the memory of the PLC. If I upload a program, and it's backwards, by the way, from computers. So normally when we these two guys are computers. This guy thinks he's the boss. So when we send information to the PLC, it's called download. When we get information from the PLC, it's called upload. So it's just opposite of what we see, right? So when you're on the internet, your computer's the boss. PLCs, this guy thinks it's the what? It's the boss. So it's opposite. So sending a program to the PLC, we call it download. And if you do it backwards, you're going to cause problems. Because if you got this nice big old program in your computer and you haven't stored it, and you accidentally upload, it's going to wipe your program out. It's going to say, "Are you sure you want to do this?" Yeah. Y'all see this all the time. These boxes pop up, and normally all we see is what? Yes. We don't read what it says. We just do what? Yeah, but if you upload a program, and you got a program in your screen that you haven't done what? That you haven't saved, then it's gone. So you better get used to this little button right there. Y'all see what this looks like? It's like a little floppy disk, which we don't have anymore. You better save it, and save it often. Over on when we take the programs we do in PLC3, the PLCs and automated systems, they're so complex, we call it the 10-rung rule. Every 10 rungs, you do what? Save. Yeah, it's just, and that happens. I mean, there's little bugs. You get people that don't know exactly what they're doing. They don't do things right. The application locks up. You ever had an application lock up? Even on your cell phone, you've had applications lock up. Usually what you do, you abort it and reload it. Well, that's what we do. So these things, these applications, you get into people, the engineers design them, then they put them into your hands, and they don't know what we do. We do things that they didn't want. They didn't expect. And so these applications locked up, if you don't save it, and you've got 500 lines of code out there, or rungs, and you don't save it and it locks up, guess what? You've lost all of it. So we don't have to worry. None of ours are over 10 rungs, so we're okay. So, and what we do on ours is we're supposed to draw it first, but what most people do is they get it running, and then they draw it because they don't want to keep erasing. But that's programming, guys. This is ladder language on every PLC that I've ever seen. All you got to do is learn syntax. So right here, I got to figure out what timer means, what time base means, what preset means, and what's accumulator. Once I know that, and then I go to Siemens, I say, oh, that's how they do it. So if you go to Teal Portal, you see it's exactly the same thing, except they address a little different. So what this does is we specify a input, we specify a slot number, and then we specify which bit within the slot we want to go to. So we got to understand binary to even understand what I just said. So very easy to address. But watch what happens if I assign it a name. So I'm going to come up here and I'm going to pull another one down. I'm going to go back to user. I'm going to pull a contact down. And now what I'm going to do is I'm just going to say input. And y'all can see what it does. It automatically fills in all the addresses for me. So originally RS Logic 500 does not require names, but we're going to use them because your new PLCs, they don't call them symbols, they call them tags. And normally what you do is you assign your tags first. And then after you assign your tags to an input or an output, then you're not dealing with addresses anymore, you're just dealing with names. So If y'all take the PLC 3, you'll learn that real fast. So we'll take the diagrams, we'll set up a tag table, and then after that we use names and we don't use numbers anymore. You'll see that? So I pull this down right here, and I want to give it the same address as that. I just come up here, instead of typing the address, I type in its name. By the way, if you notice, it's already started populating them down here for me. I gotta spell it right though. Oh, that's input 2. No matter, I messed up. So this is high-level language. I don't have to know the processor. I don't have to know the memory. I don't basically have to know just about anything. Now, on RSLogix 500, we're going to have to learn a little bit about memory, and we'll talk about what these things over here mean. So, if you get to your PLCs, you don't have this stuff right here. And we'll learn that. So there's very few differences between this. How they handle the memory, that's what's changed a lot during. But I come over here and I say, okay, I hit that and it's still got an E, right? You understand, which means it's still got some type of syntax error. Well, I could come right down here and click on this, and it tells me that I got a symbol, input 1 is not valid. So I know I don't have a symbol called 1. The only symbol I have is what? 2. So it's told me exactly what's wrong with the rung. Rung 0. We've also said I've got an operand not entered. An operand would be this information we got to put over there. So that's another term we got to learn, right? And I'm going to click on this, and I'm not going to save it. And I'll show y'all some differences. Most of your newer software requires you to enter a name of the program before you write it. This guy, RSLogix 500, for some reason, don't ask you for a name until you try to download it. So, or you try to save it. No, I'm not going to save anything. So this is ladder language, guys. I mean, this is it. This is what we're going to program in. So we don't have to worry about solenoids. We don't have, because all you're going to do is you're going to turn on an output, and then whatever you got hooked up to that output is maybe you might have a solenoid, but it's going to be hooked up to an output, right? You understand? You turn the output on, and then the solenoid energizes. And whatever the solenoid controls, that's what this is addressing. This looks like this came from a Siemens PLC because the addressing is a little different. But you notice every instruction, except for these, they've assigned it a what? They've assigned it a name. So once I assign an instruction a name, then I can use the name instead of the address. Ladder language is a high-level PLC language we'll use to program. The programming application we'll use is called RSLogix 500. It contains the translator. We'll look at the different types of translators we have. So sometimes we have an application called Simulator. It uses a different translator. So we'll look at those. A lot of terms. I'll give you a review. I mean, we'll have it. When's the test? Not. Yeah. We'll have a review out and show y'all exactly what y'all need to have. We can't really give a review to start right now because we don't know exactly where we're going to be at when it comes time for the test. So what we used to, and you can still run into these. Most computers now are programmed with a personal computer, even though there are some smaller ones that use a dedicated program. And how do we program them? We run an application. How do you understand? That's developed by the company that sells the PLC. So I mean, I couldn't use CM Portal, which is Siemens, to program one out in PLC. So to program Allen Bradley PLCs, you got to use Allen Bradley's application. To program Siemens PLCs, you have to use Siemens application. To program a little PLC that we got over there on our skill bosses, we would have to buy the application program. That's where they make their money. It's on the application. Luckily, we're an educational institution. We get cut rates, but Allen Bradley does yearly license, which means you got to do what? Yeah, about $1,000 to we get a level license for around $2,700 because we get an education package. And why do they do that? Because if you learn their language in school, you get the opportunity to buy a PLC. Those are you going to buy. Yeah. We get the Siemens PLC. We get what we call a six-pack. We have to buy them in groups of six. The PLC, a 1200 PLC, 60 PLC. We get a permanent license on our software, Portal 14 or 15. We get a little simulation box so we can use it as a trainer. And we get we get an analog output port that we can put on it. I think we get about $300. For us, y'all couldn't get it right. We have to buy them in groups of six. You have to get a six-pack. And that's it for this chapter, guys. So what are we going to consider when we look for if you had an opportunity to buy these things? Yeah. The portal, the types of ports, the portal that's available on it, right? Because you don't go buy one, expect a fixed PLC. Because if you buy the wrong fixed PLC, you're messed up, right? Because you can't do what? You can't upgrade it. If you buy one of these hybrid PLCs, which is what I call them, then you'll get so many fixed ports, right? You understand? But what can you do then? And those are probably one of the predominant ones that we have. So very seldom do we see true racks anymore. The backplane would actually, it'll be a DIN rail that you mount, and then the PLC pops onto it, and then your actual backplane runs through the PLC itself. So, and you need to know the programming application, right? You understand that you don't want to buy 4 or 5 different PLCs because you'd have to have a what? You'd have to have a different application for every one of them. This is what they've done out at US Steel. Used to they would bid them out, and they'd just take the lowest bidder, right? And of course, then they forgot how many PLCs they have out there. You don't see that very often now. Usually, like if you went down to Rosa, they only have what? Siemens. I think Flexion Gate only uses Allen Bradley. They make sure they use the same brand. That way they can only have one program to support. You need to make sure you get, if you buy one of these PLCs, you might not be able to get a lot of support. Allen Bradley has really good support. Steven has really good support. That comes with your license. So if you let your license lapse, you won't get any more upgrades in your applications. But what did you just lose? You just actually lost your support. If you call down there and wanted support, what would they do? Yeah, not that. They charge you for it. Yeah. So everybody okay? You ever seen a fixed PLC and a fixed PLC and a modular PLC? Fixed PLC, you can't add anything to it. You're stuck with the number of inputs you got. You're stuck with the number of outputs you got. You're stuck with the type of output. So you buy them according to the inputs and outputs. Syncing inputs, sourcing outputs. We need to understand that. Predominantly over here in the U.S., we use syncing inputs and we use sourcing outputs. We'll talk about what it means. That's predominant. Some PLC give you the ability to wire anyway. So 1100 PLC has groups. The first group has 0 through 3, and the second group has 4 through 9. And then they have their own column. So what you can do with those is you can wire group of 4, you can wire it sitting or forcing, and the other group of 6, you can wire it sitting. So, and we'll find out what that means. But that's whatever you want to do, right? They don't care if you're syncing, they don't care if you're sourcing, they don't care if it's AC, they don't care if it's DC. So questions?